Welcome back everyone. In this lecture I am going to actually construct irreducible representations of the symmetric group. So, for that recall the construction of m lambda. So, m lambda is nothing but C span of all the tabloids T lambda. So, now what we are going to do? We are going to actually define some linear operators acting on this space m lambdas. So, for that let us actually fix two partitions. So, this is the definition of polytabloids, which are the building blocks of our irreducible representations. So, we fix lambda and mu, they are the partitions of n, and then let us take T be a lambda tableau, and then we define this this map, let us call it AT, which is a map from mu to mu. So, T is a given lambda tableau, and with this T we are defining this AT, which is a linear operator and which is given by the following formula. So, AT is given by the summation sin pi, where pi comes from the column stabilizer of T, and then we take this phi mu, apply it on pi. Okay. So, AT of pi is defined this way. Okay. So, when we apply this on some tableau, okay, lambda mu tabloid, then we apply it here on this. Okay. As an operator, AT is just a summation pi in CT sin of pi and then phi mu of pi. So, recall that phi mu is that representation from Sn to GL of m mu. So, given pi, we denote the image by mu phi of pi. Okay. And each one of them are operator on mu. So, this is the operator that we are talking about. So, now when lambda equal to mu, so we have the images of T, and that we call it as polytabloid associated with T. So, when lambda equal to mu, then we set this ET to be AT applied on T. So, this is what we call it as polytabloid associated to T. Okay. So, more explicitly, AT obtained as follows: you take this operator AT, which is sum of sin of pi, and then we apply this phi lambda of pi applied on T, okay, for various pi coming from this CT. Okay. So, now let us rewrite this. So, what happens, this phi lambda pi on T, basically this is the tabloid T. So, when we take pi in Sn, the action of p lambda of pi on this is defined to be just pi applied on this tabloid T, which is exactly pi T. Okay. So, basically we take all possible the orbits of this tabloid under this group which is the column stabilizer of this T, and then we take the alternative sum of this, that is what we call it as polytabloid. So, this alternating sum is very important. So, that actually kind of plays an important role here. So, let me just explain like what we are indeed doing. So, we start with the tableau, let us say T is a lambda tableau. So, then the equivalence class of T is actually to obtain that what we do, we just do not care about columns, we just only focus on the rows, and then we permute the entries among the rows. So, that is how the equivalence class of this T is obtained. So, this is those tableaus S are related to T. So, that means S and T they have same set of entries in each row. And note that once I start with the tableau, let us do some example, something like this. Let us say 3, 4, 1 and then 5, 2. So, then you can see that since we are allowed to actually permute among the rows. So, I can always write each row in the increasing order. So, I can write it as 1, 3, 4 and then 2, 5. Okay. Now, what this operator this AT does, AT actually takes care of the column permutation. So, the equivalence relation takes care of the row permutation and AT takes care of the column permutation. So, in particularly, so when you apply this T and then look at this ET, so ET is going to be some sum of elements, but if you think about it, so the sum of the elements indeed comes from the column stabilizer of T. So, what is the column stabilizer here in this case? So, this is going to be S 1 4 3. So, which is same as 1 3 4, 1 3 4 and then you take a product with sorry, I am taking the column stabilizer. So, the columns are 3 5 and then take 2 4 and then this S singleton 1. So, this is what we are taking. So, in this case if we take this T to be this, then ET is going to have all possible summation the sine of pi and then pi T applied, pi applied on T and then pi varies over all possible this CT. So, in particularly in this example ET is going to be first you take the you first take this tabloid T which is given by 3 4 1 5 2 and then for example, you just minus with so S 3 5. So, let us do only for this group. So, this group will have identity and the transposition 3 5. So, if we take the transposition 3 5, so then you can see that that should be applied on this element. So, then this element becomes, so 3 goes to 5 and then 5 goes to 3 and the remaining elements will stay as it is, and this is the class that we get. So, the class of this plus some extra elements. Okay. So, now if you go into the equivalence class, then you can see that. So, this you can rewrite as 1 3 4 and then 2 5, and similarly this you can rewrite 1 4 5 and then 2 3. Okay. So, now indeed inside your ET you are also trying to do this column permutations. So, if we do that what we can do, like, so we can actually make sure that we will be able to actually write this. You can start with any tableau and then end up with the what is called standard tableau. So, the standard tableau in which the row entries will increase and as well as the column entries will increase. So, now up to the equivalence you can see that you can always write a row in the increasing form. Now, once we go to the ET you can easily see that the columns are also can be permuted. So, in a way, so that means the standard tableaus that will actually index the elements ET. Okay. So, we want to actually kind of compute the dimension of that irreducible representation S lambda and so on, but let us see like what happens indeed to that irreducible representation. So, once we have this polytabloids, then it is easy to define that S lambda. So, the S lambda is indeed defined to be the subspace of M lambda spanned by the all possible polytabloids E t with T at lambda tableau. So, this is the C span of all possible E t, where T is nothing but a lambda tableau. So, we take all possible lambda tableaus and then look at the possible polytabloids that you can get it from the lambda tableaus and then take the span of this, and this is a subspace of M lambda, and this is the space that we are interested in. And first of all, we need to realize that we have an induced action of the symmetric group on this subspace. So, for that purpose, let us see actually how the symmetric group act on E t. So, here is a lemma which tells the action. So, if we take sigma in S n and T is a lambda tableau, so then if you apply the action of phi lambda of sigma on this E t, so then what we get is exactly E sigma t. Okay. So, basically the sigma just simply permutes all this E t. So, this is how we are actually realizing that we have the induced action on this S lambda. So, note that the phi lambda is actually the action that we have defined on this M lambda, and this lemma immediately implies that phi lambda restricted to this S lambda is going to give us action. So, the way we write this, the restriction of phi lambda to from this no, we are not talking about the restriction of the group, we are talking about submodule. So, this S lambda is indeed invariant under phi lambda of sigma for all sigma in S n. So, that is what we get. So, that means this S lambda is indeed sub representation of M lambda. So, that is what this lemma actually tells. To see this, first we need to understand what happens to the column stabilizer, because E t is defined using this orbit sum of column stabilizer. So, let us recall what is E t. So, E t by definition we apply this A t on t, so which is sum of sin pi and pi t, where t comes from this pi comes from the column stabilizer of t. So, now let us compare the column stabilizer of t and sigma t, and it is easy to see that the column stabilizer of sigma t is same as the column stabilizer of C t up to conjugation. So, it is basically given by sigma C t sigma inverse. So, let us check this. Indeed, what happens if xi is the set of entries of column I of t. So, let us call it this xi. So, this is the set of entries of column I of t. So, then it is easy to see that sigma of xi is going to be the set of column set of entries of column I of sigma t. Okay, that is just obvious from the definition of sigma of t. So, that means if tau stabilizes xi, suppose tau stabilizes xi. So, then if and only if what happens, you take sigma tau sigma inverse. So, that should stabilizes this sigma of xi. Okay. So, that means that whenever tau is in C t, if and only if sigma tau sigma inverse is going to be in C sigma t. So, that proves that C sigma t is given by sigma C t sigma inverse. So, now using this, let us compute what we wanted. So, let us compute more generally this phi lambda of sigma and then this A t. So, note that both of them are operators on m lambda. So, by definition of A t, you can see that this is summation sine of pi and phi lambda of sigma, phi lambda of pi, and then pi varies over C t. Okay. So, this is just by definition. Note that phi lambda is nothing but group homomorphism. So, you can rewrite this as summation sine of pi phi lambda sigma pi, pi runs over C t. So, now what we can do, we can just simply change the conjugation. So, this is same as, so we substitute this tau by sigma pi sigma inverse. So, that means we just multiply sigma inverse and then sigma. So, then we can see that. So, this becomes exactly sigma inverse sigma. So, the sign of the conjugation is same as the sign. So, sine of pi is same as sine of sigma pi sigma inverse for all sigma and pi in Sn. So, using that, if we rewrite, so we get this as sine of pi phi lambda tau phi lambda sigma, the tau runs over C sigma t. Okay, because C t and sigma t, they are related by conjugation. So, this tells us this is exactly equal to A sigma t and then phi lambda sigma, okay, because this is by definition of A t. So, that means we have this equality phi lambda of sigma A t is nothing but A sigma t phi lambda of sigma. So, now apply that phi lambda sigma. So, recall E t is nothing but A t applied on t. So, now what we want to compute phi lambda of sigma applied on E t. So, which is going to be exactly equal to phi lambda sigma A t applied on t. Now, when you switch this, we get A sigma t phi lambda sigma and then applied on t. So, which is exactly equal to A sigma t applied on sigma t, which is the definition of E sigma t. Okay. So, this proves that whenever you apply phi lambda of sigma on E t, you get E sigma t. So, that means if we take this S lambda, which is the C span of all these E t's, where t comes from lambda tableau. So, then this is indeed an invariant subspace of m lambda. Now, note that since m lambda is actually finite dimensional representation of symmetric group. So, we have actually normalized inner product on m lambda, which is the symmetric group invariant, and we will work with that particular inner product, and in particularly we can talk about S lambda perp, which is those elements alpha in m lambda which are indeed orthogonal to all elements of S lambda. So, we fix that inner product which is Sn invariant on this m lambda, and with respect to that we talk about this orthogonal complement of this S lambda. Now, it is immediate that this m lambda is indeed a direct sum of S lambda perp. So, this is something we have, and these m lambdas, they are called spec modules. So, this was introduced by Wilhelm Speck in order to classify all possible irreducible representations. So, this we call it as spec modules. Of course, spec modules associated to lambda. And what we want to prove here is the theorem that this set S lambda, lambda partition n. So, this is exactly gives us the irrep of Sn. The irreducible representations of Sn is classified using these spec modules associated to partitions of lambda. So, that means there are two things to prove. First one is all these S lambdas is irreducible finite dimensional representation of Sn. So, that is the first thing to prove. The second thing to prove is that they are non-isomorphic copies. Okay. So, that way we know that they will have exactly the number of conjugacy classes of Sn number of the irreducible representations, and this set cannot have more than that. So, they will be equal. Okay. So, we just prove that S lambda is irreducible finite dimensional representation of Sn, and S lambda isomorphic to S mu if and only if lambda equal to mu. So, these two claims will tell you that the set of irreducible representations of Sn classified using these spec modules associated to partitions of n. Okay. To prove this, we need several observations and lemmas. So, let us actually go one by one and then try to use them in order to prove. So, but the important thing to notice is that these elements polytabloids ET, they do not need to be generally linearly independent. Okay. So, this is the most important remark, that ET aren't in general linearly independent. Okay. So, let us see an example to demonstrate this. So, we can actually look at what is called this alternating representation. So, the alternating representation can be obtained by taking this trivial partition where you take 1 1 1 of n. So, that means you have lambda to be these boxes 1 2 etc. 6. So, now note that the lambda tableaus are the same thing as lambda tabloids here, because each row has only one single box. So, the T lambda is same as the set of lambda tableaus. Okay. There is no equivalence relation because each row has only one element. So, now what happens to the phi lambda? So, phi lambda, now you can see that so since you have n boxes and tabloids are corresponding to lambda tableaus. So, that means there are exactly n factorial n factorial elements are there. So, the cardinality of T lambda. So, here lambda 1 is 1 and lambda 2 is 1 and so on, lambda n is going to be 1. And if you recall, the cardinality of T lambda is nothing but cardinality of Sn divided by cardinality of S lambda, and each one of them has 1 and 1. So, it is exactly n factorial. So, it is just a all possible permutations of these entries of lambda. So, now what is going to be the tabloid associated with this? So, T has only one column. So, because T has only one column, you can easily see that the column stabilizer of this column is going to just all possible permutations of this 1 to n, which is exactly the symmetric group. So, now what is E t? So, E t by definition it is sum of sin pi and then pi t, where pi is coming from C t, which is exactly S n. So, now recall that when you apply this phi lambda sigma on E t, so which is exactly sigma E t, which is exactly E sigma t. So, this is what we proved. Now, what we claim that this is also equal to sin sigma times E t. Okay, so, here is the claim. So, this is something we already verified. So, we claim that phi lambda of sigma applied on E t is going to be sin of sigma E t. Note that the space S lambda that we define, this is indeed S n invariant. So, that means this element E sigma t should be some scalar multiple of E t. So, that is for sure, and we are saying that explicitly that scalar is the sign of sigma. So, let us do this straight away. So, this is going to be summation sin pi t, where pi comes from S n. So, now note that this you have to apply, this is E t definition, you have to apply sigma on this. So, phi lambda of sigma. So, by definition of phi lambda of sigma, this is exactly going to be equal to sin pi sigma pi t, where pi comes from S n. So, now if you reindex the thing, you can see that this is exactly equal to, so you multiply by sin sigma and then you can include the sigma here, and then if you reindex, this is exactly sin sigma times E t. Okay, this is straightforward computation. So, that tells you that here we have substituted like tau equal to sigma pi. Okay, this we replace by tau, and tau will run over sigma S n. So, this tells us that we have only one tabloid and all other tabloids are related to the one tabloid that we have started with, E t. Okay, this means the tabloids not necessarily linearly independent. Okay, so this actually kind of gives some idea about how to work with this S lambda. So, ultimately what we want to prove, so let me make it as a proportion that, maybe this is the main theorem indeed, but anyway. So, let's make this proportion. So, which actually tells about like when you apply this operator on A t lambda on some S mu. So, that is like when it could be 0 or non-zero, it is going to decide. So, we want to decide that. So, we take lambda and mu to be partition of n, and suppose that T lambda is a lambda tableau and S mu is a mu tableau, such that A T lambda applied on S mu is non-zero. So, we fix this T lambda, which is lambda tableau, and then S mu, which is mu tableau, okay, such that you take this operator A t lambda, apply it on S mu, assume that this is non-zero. Okay. So, then we can conclude that this lambda dominates mu. Moreover, if lambda equal to mu, so then we can conclude that this A t lambda applied on S lambda. So, this is going to give us exactly plus or minus of E t lambda. Okay. So, we have this very explicit action of A t lambda on any tabloid S lambda. So, it is going to be again given by this plus or minus E t lambda. So, this is a very crucial proportion. So, which is again used using this we will prove the irreducibility of S lambda, and this proportion again comes from the earlier dominance lemma that we have proved. Okay. So, maybe like I will do the proof of this in the next lecture, and then using this we will actually conclude that S lambdas are indeed irreducibles. Okay, I will stop here. Yeah, thanks.